Okay, so we are in Generalized Linear Models with Examples in R, Chapter 1, question 7. Okay, we're in question 7. So this is a multi-parter, so we'll look at everything in turn, but we're going to load a data set called humanfat, and then we're going to go through each of the questions here. Okay, so the first thing we need to do is to get a hold of that data, and it is in a package called GLMsData. And so we need to install that package and load that package, and then I can actually get that data by calling data humanfat. And then I'm just relabeling humanfat, which is our data, as D, so I can type a little bit less, and then we'll actually look at D here. Okay, and so you see, so here's our total data set. So we have age, %fat, gender, and BMI. Okay. So the first thing we need to do is to use the names command to find the names of all of the variables or the names of the columns. Well, we've already done that, but let's just to use names. So here it is. So we have age, %fat, gender, BMI, which we've already done. And then the next question, number 2, we need to determine which ones are quantitative and which ones are qualitative. Well, we can kind of do that, right? We can, in a few ways, we can look at the data and say, okay, well, these ones are numbers and these ones are letters. So probably these ones are quantitative and this one is qualitative. That can be a little bit misleading though, because sometimes things are identified numerically, right? So maybe you have patients, so you might have patient 1, 2, 3, 4 or something. So it's a number, but it's actually, it's just a label. It's not really a number. The other thing we can do is to look at these little headings. Okay, this tells us what the data is. So this is integer, so age is an integer. % body fat is double, it's just a real number. Gender is factor, that makes it qualitative, and then BMI again is double, which just makes it a real. The other thing we can do is we can use the str or structure command, okay, and get a quick glimpse of everything. And again, we see that we have integers, numerical, which is the double, factor, numerical. Okay. For number 3, for any qualitative variables, the only one here being gender, is to define appropriate dummy variables. Okay. So later, we are going to be asked to let me make sure that I've loaded this. I don't want to make an error here. Okay. We're going to be asked to encode male as 1 and female as 0. And so I'm just going to do that here. And I do that with the if-else command. So I pass it the argument test. And so I say, if one of these entries is M for male, turn it to 1. Otherwise, turn it to 0. So the females will be 0, males will be 1, and then we'll look at that data and just see how it's changed, right? So same data, but now under gender, we have 1, 1, 1, 1. It's recoded this to double. It's really still a factor. It's not going to be a big deal as we go forward, so I just won't take care of it right now. But presumably, you may need to reconvert this into a factor, okay, or an integer or something. Okay. So now we need to summarize the variables, so we can do that with the summary function. Okay, so again, the summary function gives us each of the variables and then some information about it. If we wanted additional information like the standard deviation, we would need to use the SD command, and so I'll just do one of these here, so SD age. Okay, and that gives us the standard deviation for age. Okay, so now we need to plot % fat against each of the variables here, and then note relevant features of the data. Okay, so here we are. So the first one here is % fat against age. Okay, what are some important things here? Well, there seems to be a linear trend, but we know that it can't continue forever because % fat is going to be bounded between 0 and 1. Okay. So here we have gender and % fat. Now it's a little bit misleading because gender is either 0 for female or 1 for male, okay, because of how we coded everything. So there's no such thing as 0.2 or whatever. But anyway, this is what that data looks like. Again, the % fat is going to be bounded, so that's an important thing to know here. And then for the last one, BMI and % fat. So here's that data. And I think that in all of them, again, the important feature here is just simply that the body fat is going to be bounded between 0 and 1. Okay, so Would linear regression seem appropriate for modeling this data, yes or no? So probably not, because of what we just mentioned, which is that, the percent body fat, it's bounded. But it might give decent estimates, a linear regression, just because it might give decent estimates within within the range that is tested in the data, right? Because we do see, more or less linearity with the data, and so so within percent body fats of, call it 10 to roughly 40 or something like that for this age range, then it might, linear regression might be just fine. Okay. So now we need to, number 7 here, is read the help file and determine whether the data comes from experiment or observational study. Okay. So we'll do that. So here's the command to bring up the help file that you can see over here. So it's not really clear if this is an experiment or not. It says that the data was generated after investigating a new method for measuring body composition. So presumably there's some other method that they're comparing it to. So I guess it is kind of an experiment, but it's not an experiment in the way that is important to us here. Namely, none of the variables in our data, right? None of these variables here were controlled. These were just measured. Really, the only thing that was controlled was the way that the method that was being used for measuring the body fat. So, after reading this help file, determine which population the results can be expected to generalize to. Short form answer is that it would be, people that were represented in the sample. So if you read through this, it's healthy males and females between the ages of 23 and 61, basically. Okay. Now suppose that we fit a linear regression to the data, whether or not it's a good idea, where we're regressing percent fat on BMI. Interpret the systematic component of this model. So I'm actually going to run this, and then we'll interpret the results here. So we're going to interpret the systematic component. Okay, so in other words, the beta naught plus beta 1 x1. Okay, so the systematic component right here. So there's a couple of things. So the beta 1, so this term right here, it says that percent fat, mu, that percent fat is going to increase by an amount beta 1 for every 1 point increase in BMI. Okay, after you account for the average of, well, not average, after you account for the intercept, and we'll talk about the intercept here in a second. So what is the intercept? The intercept is the value for body fat, or for percent fat, when BMI equals 0, which is, you can't have BMI equals 0, but it's just a mathematical construct. Okay, so that's what it means. So when we actually run the regression, so here's our results. So this means that the regression predicts that that for every 1 point increase in BMI, body fat percentage will go up by about 1.7%, and that the percent body fat for somebody with 0 BMI is -11. Again, these are not realistic values. That's a mathematical construct. Okay, so now we want to do the same thing with a slightly more complicated model, where we're regressing not only on BMI but also gender, on male or female. Okay, so remember, we have males coded as 1 and females as 0. So really, gender just means maleness. Okay, so we can so let's just run this again. But now let's try to interpret first the systematic component and then actually look at the results. Okay, so what the systematic component is saying is again that it predicts that percent fat is predicted to increase by an amount beta 1 for every 1 point increase in BMI, after accounting for the other terms in the equation, namely maleness or gender, as well as the intercept. Now, similarly, it says that males will differ from females by an amount beta 2 after accounting for BMI and the intercept, and that the intercept, beta naught, represents the value For females, well, okay, so it represents the value when all of the data is 0. And 0 for gender is female, so that means for female. And when BMI is 0, right? So beta naught represents the value when percent fat, or for percent fat for females when their BMI is 0. Okay, so now when we actually run the regression, we get these results right here. Okay, and so let's actually put some numbers to these things. So so the value here for BMI says that percent body fat is predicted to go up by about 1.1% for every 1 point increase in BMI after you've accounted for gender and intercept. This says that males, remember because gender is 1 for males, have about 14%, 14.1% less body fat than females after you account for BMI and the intercept. And that the expected percent fat for females with BMI 0 is 6.3. Okay. Finally, we're asked to estimate P and P prime for the two models. So P is just the number of parameters or really predicted variables, and P prime is all of those plus the intercept, right? So for model 1, right? So for model 1, where's model 1? We're just regressing on BMI, so P is 1, okay? And then P prime, we also have the intercept, which is not noted in the R notation, but it's there, okay? It's 2, right? So P prime is 2. For model 2, we're regressing on 2 variables, BMI and gender, so P is 2, and then we have the intercept for P prime, so we have P prime is 3.